Hello everyone, thanks for joining. My name is Yuwei Liao. I am a senior research statistician developer in the IoT department at SAS Institute. Today I'm going to talk about the work we have done at SAS on non-invasive beehive monitoring through acoustic data. First, I'll give a brief introduction to the beehive monitoring project at SAS. Then I will talk about beehive acoustics and also time frequency analysis, which is a commonly used technique for acoustic signal processing. I will go in details on the time frequency analysis algorithms we used in SAS event streaming processing and SAS Via products, and show our results on general beehive state monitoring and queen and worker bee piping detection. At the end is a quick summary of our work. We all know the importance of honeybees. Our food depends on bee pollination. But maintaining healthy beehives is actually a very challenging job. It is reported that during the winter of 2018 to 2019, 37% of US beehives were lost. The annual losses exceeded 40%. Beekeepers usually monitor the status of their colonies by manual examination, which are not only time-consuming, but also disruptive to the hives. With the rapid advances in sensor technologies, and also the dropping costs of the sensors, developing non-invasive monitoring system with sensors has been more and more popular. Here in SAS, we had worked on a Connect Bee project, which is part of the SAS Green initiatives, to monitor the 4 beehives at the SAS campus in Cary, North Carolina, with different sensors through SAS IoT analytics, including weight and temperature sensors, cameras, and sound recorders. Today I will focus on the non-invasive beehive monitoring through acoustic data from the sound recorders. So what types of sounds in the beehives we are interested in? Honeybees make sounds with their wings, thoracic muscles, or breathing spiracles. The most widely known and studied sound is a queen bee piping sound, which is the sound queen bees make during the battle for the throne. Workers can also make piping sounds, but much weaker under several situations. For example, when a hive is queenless, or the hive is being invaded by an enemy pest, or when a swarm is about to leave the hive. We are also interested in the hum of the hive, the everyday hive sounds as bees perform their daily tasks. For example, worker bees thermoregulating the hive, queen bees laying eggs, nurse bees feeding the young babies and the queen, bees drawing honeycomb, fanning and flying in the hives. So to summarize, there are 2 types of sounds we're interested in. One is the background sound, reflecting how busy the beehive is. And the other is the special queen bee and worker bee piping sound, which usually indicates some important events are happening in the beehive. So how do we analyze sound signals? Digital sound signals measure the amplitude of the disturbances caused by vibration over time. This is usually the waveform we see in time domain. Sound signals are typically analyzed using time frequency analysis techniques. The most popular time frequency analysis tool is the short-time Fourier transform. From the magnitude of a signal's short-time Fourier transform, we can generate the spectrogram, which is a 2-dimensional time frequency heat map of the sound. There are other ways of generating the time frequency heat map. The parametric power spectral estimation method is one of them. It has certain advantages over the short-time Fourier transform. I'll talk about how we utilize these methods in our analysis later. On the right, you can see an example of the time frequency heat map of queen bee piping sound. The x-axis is time in seconds. The y-axis is frequency in hertz. It shows clearly how the sound signal changes over time in the frequency domain. Very similar to human speech. The piping sound has strong fundamental frequency and its harmonics. The harmonics are integer multiples of the fundamental frequency. If we can reliably detect these frequency components, then we will know when queen bees are piping. Given the importance of the timely recognition of changes in queen status, we conducted an experiment to understand the dynamics of the colony hum when the queen is gone. We recorded sounds in a newly made colony, a split, that was purposely made queenless. The data was recorded continuously for 21 hours at sampling rate 48 kHz. The new hive had eggs from 1 to 3 days old, so the worker bees could make their own queen as soon as they realized they were queenless. So our research questions were, how does the hum of the hive change over time? How long does it take for the bees to realize they have no queen? Can we tell when they figure out there's no queen? This diagram shows how we process data for general beehive state monitoring. The recorded sound data is streaming in through SAS event streaming processing product. The original recorded 48 kHz data is low-pass filtered and downsampled to 1/4 of the original sampling rate, now at 12 kHz. Then we apply the short-term Fourier transform to the data to generate the spectrogram, which is a two-dimensional time-frequency representation of the sound. The next step is to apply the robust principal component analysis, RPCA, to the spectrogram to generate a low-rank matrix and a sparse matrix. Features can be extracted directly in the frequency domain by calculating the median over short time windows to generate a new two-dimensional heat map, or apply the inverse Fourier transform to the low-rank matrix or the sparse matrix to retrieve the background sound or foreground sound of interest. In case you're not familiar with RPCA, I'll describe it in a bit more detail here. Robust Principal Component Analysis, RPCA, is a matrix decomposition method that decomposes an input matrix into a low-rank matrix and a sparse matrix. RPCA is used quite extensively in video surveillance applications to separate the background, which is mostly contained in the low-rank matrix, from the moving foreground, which appears mostly in a sparse matrix. In our case, RPCA applied to the spectrogram is quite successful in separating the background and foreground sounds in the beehives. Here we have two examples. One is a frantic bee sound, and the other is a worker bee piping sound. By applying RPCA to the original spectrogram, you can see the sounds we're interested in show up in the sparse matrix, but not in the low-rank matrix. In order to monitor the general state of the beehive, we calculate the median over every 10 millisegments of the low-rank matrices across the whole 21-hour recording time to generate a new heat map, which is shown on the left. This heat map shows how the activities change over time in the beehive. For example, there's increased noise starting around 5:30 p.m. and settling down at sunset around 8:20 p.m. when the worker bees come home for the night. There is quieting time at night and activities resume as the sun rises. On the right is the same heat map but with the number of worker bee pipings detected, the black line, laid on top of the low-rank heat map. We can see that most of worker piping sounds happened within the first 2.5 hours and stopped 6 hours after the split occurred, when all hope of finding a queen bee must have been completely lost. To summarize, the combination of time-frequency analysis, specifically the spectrogram, and robust principal component analysis, we can generate results that effectively monitor the general condition and activities in the beehives. As mentioned earlier, both queen and worker bee pipings may be indications of important events in the beehives. Next, I will talk about how we reliably detect these sounds. As shown in this diagram, the recorded sound data is still streamed in, low-pass filtered and downsampled. Here we use a different algorithm called parametric power spectral estimation method to estimate the frequency spectra of the sound signal over time. Then we apply an adaptive spectrum magnitude adjustment method to balance the magnitudes of the high frequency and low frequency components. At the end, a peak finder is used to reliably detect the fundamental frequencies and the harmonics of the piping sounds. Now let's look at what is parametric power spectral estimation and how it is different from Fourier transform-based time-frequency analysis methods. The parametric spectral estimation method models the sound signal as the output of an autoregressive moving average system driven by white noise, so the estimation of the power spectrum becomes essentially the estimation of model coefficients. The advantage of the parametric spectral estimation method is that it generates much less noisy frequency spectrum than that of non-parametric methods, for example, short-time Fourier transform. As you can see in this example of queen bee piping sound here, the left is a spectrogram, which is the time-frequency heat map generated by the short-time Fourier transform. On the right is the heat map by using the parametric spectral estimation method. It has high contrast, and the frequency components we're interested in show up much clearer. Also, you might already notice that the magnitude of the high-frequency components are much lower than those of the low-frequency components, which makes it challenging to set thresholds to detect frequency peaks that we're interested in. So what can we do? To compensate for the magnitude difference, we used an adaptive spectral magnitude adjustment method. By first calculating the average spectral magnitude across windows, this curve is shown on the left. You can see that the average magnitude drops fast as the frequency increases. We generate a magnitude adjustment curve, which is proportional to the inverse of the curve on the left, to adjust every frequency spectral curve. Here we have two examples showing how the adjustment method effectively balances the magnitudes of the frequency components. On the top is an example of the queen bee piping. On the left is the spectral curve before the adjustment, and on the right is after the adjustment. The second example is the worker bee piping sound before and after. You can see that magnitudes of the frequency peaks are much more uniform now. The effect of the magnitude adjustment can be seen even better by looking at a two-dimensional time-frequency heat map before and after the adjustment. Again, the top is the queen bee piping example, and the bottom is the worker bee piping. Since worker bee piping is relatively weak, from what is highlighted here, you can see that the fundamental frequencies and their harmonics are much enhanced by this method. The last step is to use a peak finder algorithm to find all peaks above pre-trained threshold. The peak frequency between 400 and 500 Hz is identified as the fundamental frequency, marked as a red cross on the left. Then we use linear fitting to find all peaks that occur at the integer multiples of the fundamental frequency as harmonics. Once piping sounds are identified, alerts can be sent to the beekeepers to let them know that some important events might be happening in the hives. To summarize, we have talked about the Connect Bee project at SAS, in which we try to do non-invasive beehive monitoring through acoustic data. We discussed in detail the new time-frequency analysis methods for general beehive state monitoring and queen and worker bee piping detection. All methods are available in SAS event streaming processing and SAS Via products, in case you are interested to try and build your own solutions. Thanks for watching.